Proxima Centauri, the closest star to our planetary gathering, has long been a subject of interest for space specialists. This small red individual was discovered in 1915 by Scottish space master Robert Innes. It is fundamental to the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity just 4.24 light-years away, Proxima Centauri remains imperceptible to the naked eye due to its low brightness. However, Proxima Centauri holds enormous scientific significance, especially as the host star of Proxima b, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri and its cousin Tidal are more modest, cooler, and far longer lived than stars like our Sun. Their low luminosity makes them difficult to observe, but it also suggests that their habitable zones are much closer to the star. For Proxima Centauri, this means an orbital distance of approximately 0.05 astronomical units, just a small fraction of the distance between Earth and the Sun. This proximity exposes Proxima b to significant stellar activity, including regular solar flares and high levels of radiation, making its climate vastly different from Earth's. The discovery of Proxima b was a huge breakthrough in exoplanet research. Using the radial velocity technique, space experts identified subtle wobbles in Proxima's Centauri position caused by the gravitational pull of an orbiting planet. These wobbles allowed scientists to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the presence of Proxima b, marking a significant leap forward in the quest for potentially habitable worlds beyond our nearby solar system. While ground-based observations have provided valuable insights into Proxima b, they come with significant limitations such as atmospheric distortion and light interference, which hinder the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Most of the information we have, including its mass, distance from the star, and orbital characteristics, comes from indirect measurements to uncover further insights into Proxima b's environment and its potential for life. Advanced observational tools like the James Webb Space Telescope JWST are essential. Proxima Centauri and Tidal role as a gateway to understanding exoplanetary systems couldn't be more significant. As the closest star system to Earth, it offers a unique opportunity to study the conditions crucial for life. Proxima b in particular presents an enticing possibility, a rocky Earth-sized planet with the potential to harbor water and perhaps even life. However, the challenges posed by its harsh environment make it a complex puzzle for researchers. The James Webb Space Telescope is not just another tool in the arsenal of space science. It is a revolutionary instrument designed as the successor to the Hubble Space Telescope. JWST was built to overcome the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided significant insights into the universe, including the age of the cosmos and the discovery of thousands of galaxies, its capabilities are limited by its focus on visible and ultraviolet light. JWST, on the other hand, is designed to observe the universe in infrared frequencies, allowing it to peer through cosmic dust and reveal features hidden from Hubble. One of JWST key design features is its primary mirror, which spans an impressive 6.5 m in diameter, more than twice the size of Hubble's mirror. This larger mirror enables JWST to collect much more light, making it capable of observing even the faintest and most distant objects. The mirror is coated with a thin layer of gold to enhance its infrared reflectivity and is made up of 18 hexagonal segments that work together to form an extraordinarily sensitive observational platform. Another remarkable advancement is JWST layer of sun shield, which keeps the telescope's instruments at a stable temperature of about minus 233 degrees Celsius. This ultra-cold environment is essential for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second range point, L, to a stable position about 1.5 million km from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. JWST can focus on everything from the earliest galaxies to the atmospheres of exoplanets like Proxima b. Its ability to detect infrared light is especially significant as it allows scientists to study red-shifted objects, those whose light has been stretched to longer wavelengths. As the universe expands, JWST capabilities extend far beyond mere observation. It is designed to answer some of the most fundamental questions in science, including the origins of galaxies, the formation of stars, and the conditions that could support life on other planets. With its advanced instruments, including the near-infrared camera, NCAM, the mid-infrared instrument, MIRI, and the near-infrared spectrograph, JWST is not just a telescope, it is a time machine, a research laboratory, and a symbol of human ingenuity. Proxima b has captivated both scientists and the public as a potential second Earth situated within the habitable zone of its star. The planet has the right conditions to support liquid water, an essential component for life as we know it, with a mass roughly 1.17 times that of Earth. Proxima b is likely a rocky planet, comparable in structure to our own. Its proximity to Earth, just a little more than 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima b is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual sunlight while the other is in eternal darkness. This creates a unique environment with extreme temperature contrast between the two hemispheres. The region where day meets night, known as the Terminator line, could offer a limited habitable zone with conditions mild enough to support life. The challenges presented by Proxima b's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can release bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima b retains any atmosphere, it likely requires a strong magnetic field to protect it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists remain optimistic about the potential for life on Proxima b. The planet's location within the habitable zone suggests that liquid water could exist either on its surface or in subsurface reserves. Life may adapt to the harsh conditions just as Earth. Organisms thrive in extreme environments, such as deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or novel biochemical cycles. The search for life on Proxima b is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions: are we alone in the universe? Proxima b represents an enticing possibility, a rocky Earth-like world that could harbor the conditions necessary for life. As our technology advances, so too does our ability to explore this fascinating planet and uncover its secrets. While Proxima b presents enticing possibilities, its environment is heavily influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf smaller, cooler, and significantly less luminous. Its reduced size and temperature mean that its habitable zone is much closer, pulling Proxima b into an orbit just 0.05 astronomical units from the star, about 20 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet and any potential life it might harbor. One significant issue is Proxima Centauri's stellar activity, particularly its intense and frequent solar flares. These flares are sudden, powerful bursts of energy that release high doses of X-rays and ultraviolet radiation. Such events are far more common and intense in red dwarfs than in stars like our Sun. For Proxima b, this means a constant influx of high-energy particles that could strip away the planet's atmosphere over time. Without a protective magnetic field like Earth's magnetosphere, any atmosphere on Proxima b would be vulnerable to erosion, leaving its surface exposed to harsh radiation. Even if Proxima b retains some of its atmosphere, the radiation from Proxima Centauri presents significant challenges to life. High levels of ultraviolet radiation can break chemical bonds, preventing the formation of complex organic molecules. This would severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Daku's radiodurans have developed mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima b might also adapt. However, the level of radiation resistance required would be extreme, possibly necessitating entirely new biochemistries. Interesting ly Proxima b's tidal locked nature could offer some protection, while one side of the planet faces constant radiation from Proxima Centauri. The dark side could act as a refuge. Subsurface habitats or deep caves could shield potential life forms from the worst of the radiation. Additionally, if Proxima b has subsurface oceans, they could provide a stable, radiation-free environment where microbial life could thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, scientists remain hopeful that Proxima b's extreme environment offers a fascinating opportunity to study the resilience of life by observing how organisms could survive or even thrive under such conditions. Researchers can expand their understanding of what makes a planet habitable. Proxima b is not just a potential home for life, it is a laboratory in the search for life's resilience across the cosmos. The possibility of life on Proxima raises more questions than it answers, but it also offers a new perspective on the definition of habitability. The search for life on Proxima b is not only a scientific mission, but also a philosophical one. It challenges our understanding of what constitutes a habitable environment and broadens our search for life to include planets with extreme conditions. Proxima b's hostile radiation environment and tidal locking force researchers to rethink the traditional concept of habitability, which was mostly based on Earth-like conditions. One of the key aspects of studying Proxima b is its potential to reveal new insights into how life could adapt to harsh conditions. If life can indeed survive and evolve in such an extreme environment, it could redefine our expectations for where life might exist in the universe. Understanding these possibilities may help scientists focus on other exoplanets that share similar characteristics to Proxima b, expanding the criteria used to identify potentially habitable worlds. The exploration of Proxima b also fits into the broader context of the search for exoplanets, planets that exist outside our solar system. In the past few decades, the discovery of exoplanets has exploded, with thousands of these distant worlds now identified. The study of these planets, particularly those in their stars' habitable zones, has shifted our perspective on the likelihood of finding life elsewhere. Proxima b, with its proximity and potential for liquid water, is one of the most exciting candidates, but it is far from unique as technology advances. The number of known potentially habitable exoplanets continues to grow. In addition to studying Proxima b, astronomers are focusing on planets around other stars, particularly those that share characteristics with our Sun. These Sun-like stars offer habitable zones that may be more stable and conducive to life. However, Proxima b, orbiting a red dwarf star, offers a contrasting case that challenges traditional thinking about habitability. Its study can provide valuable lessons on the resilience of life and how it might exist in more extreme environments. Proxima Centauri, the star that hosts Proxima b, also offers researchers an intriguing opportunity to better understand stellar behavior, particularly the differences between stars like our Sun and red dwarfs. Red dwarfs are far more numerous in the universe than Sun-like stars, and studying these stars can help us understand how different types of stars influence the potential for life on surrounding planets. Proxima sense frequent stellar flares and the effects of its intense radiation on Proxima b's atmosphere may help scientists learn how different kinds of stellar activity impact planetary environments, providing vital clues for the search for life elsewhere. For now, Proxima b remains a mystery, but technological advances and future space missions may eventually provide the data needed to answer one of the most profound questions humanity faces: is there life beyond Earth? With each new discovery, the possibility of finding life on Proxima b or other exoplanets becomes more plausible, and the implications of such a finding would be profound. The search for life beyond Earth continues to evolve, and Proxima stands as a beacon for future exploration. The potential for discovering extraterrestrial life on adapt to extreme conditions such as intense radiation and temperature fluctuations. If microbial life or even more complex organisms exist or could survive there, they might possess unique biological adaptations that allow them to withstand these hostile conditions. Research into extremophiles organisms on Earth that thrive in extreme environments, such as those living near hydrothermal vents or in acid lakes, could offer valuable insights. These organisms rely on unconventional biochemistry to survive, and similar adaptations might be found on Proxima b, suggesting that life elsewhere in the universe may not need to mirror life on Earth in order to thrive. Another avenue of exploration involves studying the planet's potential magnetic field. A strong magnetic field is crucial for protecting any atmosphere from being stripped away by solar wind and cosmic radiation. If Proxima b has such a magnetic shield, it would significantly enhance its chances of maintaining a stable environment capable of supporting life. Recent advancements in space-based instruments that can detect faint magnetic fields could help scientists understand the composition and dynamic of Proxima b's atmosphere, providing more clues about its potential habitability. Looking beyond Proxima b, the study of red dwarfs and their planets opens up broader implications for understanding planetary systems. Red dwarfs are the most common type of star in the Milky Way, and many potentially habitable exoplanets orbit these stars. By understanding the relationship between red dwarfs and their planets, astronomers may be able to refine their methods of detecting habitable planets around other stars, increasing the likelihood of finding life elsewhere in the galaxy. The quest to understand Proxima b and its environment is not just about one planet, but rather about the broader context of life in the universe.